So therefore, in most of the approaches that has been proposed to construct a quantum computer, it has lots and lots of errors. This qubit is very, very fragile and very unstable, and it's very easily collapsed into a classical qubit. So therefore, it's a daunting number that for one useful logical qubit, you have to use 10 to even perhaps 100 error-correcting bits to correct one useful qubit. And that obviously is very, very, very difficult to scale. And that's why we don't yet have a truly functional quantum computer yet, which can factorize a very big number. Now enter my scientific discovery. So we discovered this mysterious but very interesting angel particle, which is half of a regular particle. So then, so it's a little bit complicated scientific diagram, but somehow when you enter in with one qubit, which is a regular particle, it can be immediately split into two of these Majorana fermia, or these angel particles. So then each being half. So one qubit you already think is the minimal thing you can have, but one qubit is now stored in two angel particles. So just like one qubit entering here, it's partially stored here and partially stored there. Then if you have local perturbation, it's very hard for local perturbation to destroy the global, these two angel particles together function as one qubit. So it's very, very hard for local perturbation to destroy this qubit. And therefore, it's a very, very robust way of doing computation. In fact, in this experimental measurement, what is happening is that these angel particles are braiding with each other. So if you have some lines and if you try to braid them, that is kind of a digital operation if you either braid it or you didn't. Whereas in most other approaches to quantum computing, it's almost an analog computation. You can very easily make little errors. But if you do what is called a topological operation of braiding, then then it's actually very, very robust. So in our approach, one qubit is just one qubit. You don't need error-correcting qubits. So this is still, after our discovery, it's still kind of a new approach. So it's coming up. But compared to other approaches, which may already have many, many qubits, but a lot of them are serving as error-correcting qubits to one useful qubit, I believe our approach will eventually scale up much, much faster because it's one-to-one.
Thank you for your time. So my question is, when do you think quantum computing would be in the application, like after your findings and research? And when it is in the application, do you think it's going to be in the hands of only big certain companies, or will it scale into having quantum research?
So I think quantum computing research, most ideally, should be done in open environment. I think because let me just make this statement because I know a lot of companies are trying, but the very nature of company trying is they have to protect shareholder interest, they have to protect the secret. But for something so powerful and its implication for humanity so unknown, that I think it should be best conducted in open university research. And this is exactly what I'm doing. So my approach to a quantum computer, I have many, many temptations to do a company on quantum computer, but I resisted that.
And what is your prediction of application of quantum computing?
With or without my invention? I think if you use this old way of, way of trying, it will take a long, long time.